Okay, example number 3. Alright, so it says find the dimensions of the rectangular box of maximum volume such that the sum of the lengths of its 12 edges is a constant c. So when we add up all 12 of the edges of the box, so we'll kind of sketch a box here. So sketching a box, and we're going to have 12 edges of this box. So without drawing the other side, you can see how you got 1, 2, 3, 4, 1, 2, 3, 4 on the back, and then 1, 2, 3, 4, 1, 2, 3, 4. So all these edges right here, whatever they are, have to add up to a constant c, and we want to maximize the volume such that that's the case. So we can call this y, call that x, call that z, and hopefully you guys remember that the volume of a box is length times width times height, which in this case is x, y, z. Now, if you do remember from calculus ABBC, when you maximize the area, when it was just like the area of a rectangle, the maximum area of the rectangle was a square. So we should probably assume, and we'll just write this over here, we should assume, and we could be wrong about that, but we'll assume that x equals y equals z is going to maximize the volume of this thing. So basically we're looking at a cube if that's the case. We'll see. We'll see if this is right at the end. So what we have to do is we have to come up with some kind of an equation that's going to help us to maximize this, because this is our equation that we're trying to maximize, but we need a secondary equation so that we can get this thing down into two variables. So it looks like, well, this right here is the length of y. This piece right here, this edge is the length of y. This one on the back here is the length of y, and then the one below it down here, which isn't sketched, is the length of y. So it looks like I got 4 of those. And I got 1, 2, 3, and then the one below that over here, 4 x's. So let's write this in the right order. And it looks like I'm going to have 4 z's, right? 1, 2, 3, 4 of those length is z. And according to this, all 12 of those edges have to add up to a constant c. So that's what we're looking at here. This is our secondary equation that we're going to be able to use to reduce this one down to two variables. So let's see what we can do here. We can divide a 4 out. X plus y plus z equals whatever our constant was over 4. And then again, we can pick any one of these variables. I'm going to choose again to solve for z. So z is going to be c over 4 minus x minus y. And then I'm going to be able to use this um, to go ahead and plug back into here to reduce this into two variables. So our new volume equation is going to be x times y times c over 4 minus x minus y. And let's go ahead and distribute that. I'll just make it easier to take the derivative. So that'll be c over 4 xy minus x squared y minus xy squared. This is the volume equation that we'll use to go ahead and take our partial derivatives. Alright, so I believe that took care of steps 1, 2, and 3. So let's take care of the partials, or maybe it was just 1 and 2. I can't remember off the top of my head here. Let's see. So the partial of this thing with respect to x. There's the x. The rest of these are constants. So that'll be c over 4y. Partial of this one with respect to x will be minus 2xy. And the partial of this one with respect to x is just going to be that minus y squared there. And we'll have to set that thing equal to 0. Now, could I try and solve this thing directly for x? Yes, I could. But what I should see is that I have a y in common here, right? So I can factor a y out. So I've got c over 4 minus 2x minus y equals 0. This is your zero product property, right? It's one factor and another factor that both have to multiply to 0. So either y is going to equal 0, or c over 4 minus 2x minus y equals 0. And here's the good part. We can get rid of this. If y equals 0, that means this length right here is 0, which means my volume would be 0. That's obviously not going to maximize anything. It's going to minimize it because you won't have any volume. So y equaling 0 is not even a factor in this case. The second one, however, will work. So this one I can solve for y. Just add y to both sides, and we're going to get that y equals c over 4 minus 2x. And then once I take the partial derivative of y, then I can use that to plug in. So let's go ahead and do that. Partial with respect to y of this thing right here is going to be c over 4 x minus, let's see, the partial of this part with respect to y is x squared. And the partial of this part is going to be minus 2xy. And we'd have to set that equal to 0. Once again, in this case, you can factor out an x. It doesn't look so good. Let's try that again. So let's factor out the x. We should have c over 4 minus x minus 2y equals 0. Once again, the x equals 0 part right here doesn't even matter because that would minimize the volume. But the c over 4 minus x minus 2y equaling 0, that does matter. So we'll have c over 4 minus x minus 2, and then I'm going to plug that stuff in right there for y. So c over 4 minus 2x equals 0. And now we can solve for x. I have this down into terms of one variable. Remember that c is a constant. So c over 4 minus x. Multiplying this throughout, we're going to get negative, let's see, 2c over 4 is a half of c. And then negative 2 times negative 2x will give us plus 4x. So let's see, combining the x's, we'll get 3x. Combining the c's, that's c over 4 minus c over 2. This is the same as 2c over 2, so it's going to give us negative c over 4 equals 0. Adding c over 4 to both sides. And then dividing by 3 gives us that x should equal c over 12. And now that we know that x equals c over 12, let's plug it back in. Right back up here. So y is c over 4 minus 2x. Y equals c over 4 minus 2x. So y is going to be c over 4 minus 2 times c over 12. So that's going to be c over 4. 2 over 12 is a 6, so we get minus c over 6. In terms of twelfths, let's see, that would be, let's see, multiplying by 3, so it's 3c over 12 minus 2c over 12, which is 1c over 12. And now we have x and we have y. Whoops, too far. So I have x equaling c over 12, y equaling c over 12, and then we can take both of those values, plug it back in all the way back up here at the top. Z is c over 4 minus x minus y. So z is c over 4 minus x, c twelfths, minus y, c twelfths. And c over 4 again is going to be, what is that, 3 over 12? So we get 3c over 12 minus c over 12 minus c over 12, which is going to give us 1c over 12 or c 12. So it does actually make sense because we got x, y, and z to all be exactly the same value. So I think, let's see, let's make sure we answer the question, the last part, which is find the dimensions. So the dimensions of the box are going to be c twelfths by c twelfths by c twelfths. The only c that actually looks like a c is that last one. Let's make that right. So here are the dimensions of our box that's going to maximize the volume, assuming that all of the legs have to add, all of the sides have to add up to C. Okay, next example, similar, very similar because we're dealing with another box here, but not exactly the same. So a cardboard box without a lid is to have a maximum volume of 32,000 cubic centimeters. Find the dimensions that are going to minimize the amount of cardboard used. So we're using cardboard to create some kind of a box that has 32,000 cubic centimeters. That's some big cardboard when you think about it. So again, kind of draw our box. Let's go the other way this time. Now the difference here in this box is that there's no lid. So this top piece is gone. We have the sides, but we do not have the top. And we do have the bottom, so as a matter of fact, let's kind of sketch in the whole thing there. Close enough. All right, so here's our box. Again, we know that volume typically, in this case, is written as XYZ. And in this case, our volume has to be 32,000. That much we know. But our secondary equation here is going to have to do with the surface area because we're trying to figure out the amount of cardboard used. So let's think about this. The surface area, so if this is X, this is Y, this is Z, we have a surface area of this piece right here in front, which is X times Z. We've got two of those, right? So we're going to have two XZs. So our surface area will be 2 XZs. I have two of these side pieces right here, and right here. That's a YZ, so I'm going to have two of those. And then I'm only going to have one bottom, the base of this thing, because the top it says it's doesn't have a lid. So it's going to be an XY, so just one of those. So the easiest thing to do would be to solve this for one of these variables, x, y, or z. Once again, I'm going to go ahead and solve for z. Doesn't really matter, although in this case I think it's going to be easier. So z is going to equal 32,000 divided by xy. And that I can use to plug into each one of these z's right here and go ahead and reduce the surface area into two variables. So the surface area is going to be 2x times 32,000 over xy plus 2y times 32,000 over xy plus xz. I'm sorry, xy. So before I even try and take partial derivatives, let's simplify this a little bit and let's make it easier to take partials. So 2 times 32,000 is 64,000. Gonna have some big numbers to deal with, but that's okay. X over x will go away, and then I'll have a y in the denominator, but let's make that a y to the negative 1 to make it easier. Same deal here. We're going to have a 64,000. Y over y will go away, so we'll have an x to the negative 1, and then plus xy. Okay, so now we're to the point where we can take partials. The partial with respect to x of our surface area. So you bring this out to the, oh no, actually that's 0, right? Only a y in there, 0. So bring this one out to the front, we get negative 64,000 x to the negative 2. And then the derivative here is just going to be plus y equals 0. Easy enough to solve this for y. We're just going to add this to both sides. So we get that y equals, what is that, 64,000 x to the negative 2, which is the same as over x squared. So let's go ahead and take the partial with respect to y. Pretty much the same thing here, except this term is going to go away, so it'll be a negative 64,000 y to the negative 2. And then the derivative of this one is plus x equals 0. Alright, so this is the same as negative 64,000. Here, let's just rewrite this. Negative 64,000 over y squared plus x equals 0. This is y, so it's going to go in here. So let's see, we're going to get negative 64,000 over this whole thing squared. So 64,000 over x squared squared plus x equals 0. Alright, I think the best option is going to be, let's add this whole thing here to both sides. So we're going to get that x equals 64,000. Now we can write that over 1, and then when we bring that up, flip it over and multiply, we're going to get x squared over 64,000, that whole thing, squared. So x, let's see, it's going to be 64,000, but that's 64,000 squared, so it's 64,000 times 64,000. That one will cancel with one of those, leaving a denominator of still 64,000. And then this x squared squared is x to the 4th. So now we should be able to solve for x. Let's multiply both sides by 64,000. Now the one thing you don't want to do normally in a circumstance like this is you don't want to divide the x out, because when you do that you could possibly be losing a solution. So let's go ahead and actually subtract 64,000x to both sides, creating this equation. And then we can factor an x out. That way we're not losing a potential solution there. So now splitting this up, setting each one equal to 0, we either get that x equals 0, which, again, in this case, really wouldn't make any sense, because if x is 0, you have no volume at all. And that means, well, obviously you've minimized your cardboard, but you have no volume, so it doesn't really make any sense. So that one's out. But this one, x cubed minus 64,000 equals 0, or x cubed equals 64,000. And if you think about it, I don't know if you can do this one in your head or not, but if you kind of don't worry about the zeros there and you get x cubed equals 64, well, the cube root of that would be 4. But I have these 3 zeros on there. Well, in order to multiply something times itself 3 times, I would have to have a 0 on here, because every time I multiply that, I'm going to add a 0. So 40 times 40 times 40 would give me those extra zeros. So the cube root here is going to be 40. So x would have to be 40. And now that we know what x is, we can go ahead and plug that back in. Where's the equation with just y in it? Where'd it go? Oh, here it is. So we're going to plug 40 back into here. So 64,000 over 40 squared. 64,000 over 40 squared. 40 times 40 is going to be 1600. Let's see, canceling out the zeros. That leaves me with 640 over 16. 16 goes into 64 4 times with an extra 0, so we also get that y equals 40. Now you might expect that z is going to equal 42, but that's not necessarily the case because you have to remember up here we did not have a top to this thing, so it's not necessarily going to be that those dimensions are going to hold to be exactly the same all the way around. Let's see. So z, let's come over here, give ourselves a little room. Knowing that x is 40 and y is 40, the original z equation is right up here, which we'll use. So 32,000 divided by x times y, 32,000 divided by x times y, 40 times 40, once again is 1600. So getting rid of the last two zeros, 320 divided by 16. 16 goes into 32 twice with an extra 0. So in this case, z is actually only 20. So what we have, let's make sure we answer the question, are, let's see, we want to find the dimensions that minimize the cardboard used. So the dimensions, in this case, are going to be 40 by 40 by 20. And it is kind of important that we know that this 40 by 40 are our x and our y. That's the base. And the reason that we know that is because the base was only used up here one time. And that's our x and y value here. So that's actually the base. You can actually write that potentially. There we go. And this part right here was our height. That's your z value. And let's see, I think it was centimeters, so that would be in centimeters cubed. And there we go. All right, it took a little bit longer than I wanted you to get through that. We only have one more example, but it is a relatively lengthy example. So I'm going to stop this one, and we will come back with one more video for problem 3.